Okay, so another great application is memorization, not memoization, but memorization. Um, uh, Now they're actually calling. I mean, this really is the word they're using, memoization. They're making a memo, um, but you can also think of it as memorization. Um, in other words, we're going to remember what these things are. So the Fibonacci sequence. Well, I'm going to go back to 18, chapter 18. We had mentioned recursion early on, and there's a whole chapter on recursion, but mostly, I just want to show this idea of the recursion, how. So, remember the idea with recursion is simply that I'll define a function, but the function is defined in terms of itself, right? So if I want the Fibonacci number of 5, then what I do is I take the Fibonacci number of 4 and add it to the Fibonacci number of 3. Oh, but what are those? Well, they call this and call that, and so it just keeps calling itself. How does it finally end? Well, here, if n is less than or equal to 1, it just returns n. So if I ask for the Fibonacci number of 0, it would return 0. If I ask for the Fibonacci number of 1, it would return 1. And so then if I ask for the Fibonacci number of 2, it would come in here and ask, it would say, well, Fibonacci number of 1, well, that's 1. And then plus the Fibonacci number of 0, which is 0. And so it would give me 1 plus 0 and return a 1. And now what they do is they actually clock this thing. So here they're going to show how long it takes. So I took this code here, and so this is just, we're not going to worry about the timing package and all that, but it is kind of nice if you want to see efficiencies. So we'll just do it this one time. So here I've got that naive recursive definition of the Fibonacci sequence, and I'm going to do 35, so that means I need to do 34 and 33, and then I'll need to do for 34 I'll need to do 33 again, and 32. So there's a lot of rehashing going through here over and over, and we can see I'll run it again here. It takes a little bit, and it took 5.42 seconds of computer time, and it had a noticeable pause, and there's the answer. 9,227,465. Okay, so if we go back to this memoization, what they're going to do is they're going to create a dictionary, and they're going to call it already known. And so notice this serves as, if I get 0, I return 0. If I get 1, I return 1. So you see it creates that dictionary of the values. And if I go into this new definition, so if n is not in already known, so if it's not 0 or 1 to begin with, then it will create a new value, and notice it looks recursive here. A fib of n minus 1 and n minus 2. But it makes a difference. It says update the already known, add a new key with that n and a new value. Okay, so it will it will add that new value. Now the thing is, let's look at if this is a 2. What happens? Well, this comes in and 2 is not already known, it's not there. And so it will create a new value, and it will do Fibonacci of 1. Oh, but we've got the answer to that, that's 1, plus Fibonacci of 0. We've got that answer, that's 0. So it'll take 1 plus 0, get a new value of 1, and it will make already known of 2. It will add in there a 2, colon, and a 1. Now, if we have a number that's already known, it just returns that. Now, notice though what happens if I do say Fibonacci of 5. Okay, 5 is definitely not in there to begin with. Now, it'll come in and it'll say I need Fibonacci of 4, Fibonacci of 3. Okay, well, those, notice though, it doesn't go to new value yet. First, it does Fibonacci of 4, and so it will call this again and say, well, what's Fibonacci of 4? Well, it is Fibonacci of 3 plus Fibonacci of 2. Well, neither of those are in there, so it will, when it goes to Fibonacci of 3, it comes in here and does 3. 3's not in there, so it will do Fibonacci of 2, Fibonacci of 1. Well, the Fibonacci of 2, it will come in here and create that and create a 1 from that. So now Fibonacci of 2 is known. Fibonacci of 1 was known. It will create a new value. Okay, so it'll be done with that Fibonacci, but we still had these others to go. But you see, it will create these already known values as it goes, and we'll see how much faster it is. So remember, this one took 5.42 seconds. If I come in here, click on that and run this one, that looked almost instantaneous. It said 0.00 seconds, so it was less than 1/100th of a second to produce that same number. Okay, so what I'm going to do is, let's see, let's try printing some things. Okay, so we're going to return the already known n. Maybe we'll do it inside here. Yeah. We'll do, we'll print let's print n, and we'll give it a little space here, and then let's print our Fibonacci of n minus 1. I haven't tried this, so I'm not sure what it's going to look like, but I thought it might be illuminating. And then Fibonacci of n minus 2. So there we have n, and we'll notice that, you know, so we're going to start with 35. Then this will be 35. That's definitely not in there. You know, so what's going to print? Is it going to start with 35? Well, it's going to print a lot of stuff. Well, let's run it and see what happens. Is it actually, you know, so it started at n equal 35, but the first thing it evaluated that was not in there was 2, and then it evaluated 3, then 4, then 5, then 6, but it only did it once each time, and that's the key. It only had to do these once each time, and this smart use of dictionary here in this recursive definition, it just built it up one at a time till I got to 35. And this time, because I was printing, it took 3/100ths of a second, so it took a little longer because I printed all that out. Okay? So, you can really think about this as to, how it's printing things out. But so it originally came in, it said 35. 35 is not already known, so I had to come in here, and it recursively, it actually tried 34 and 33, and then 33 and 32, 31 and 30. It tried all those, but it wasn't until it got down to actually 1 and 0 that it could actually do anything, because those were in there. And then it kind of worked its way back up with 2, and then 3, and then 4. And we see what it did. And so that is another great application of dictionaries, way faster, right? 3/100ths instead of 5 seconds. So 300, if it was 100 times slower, that would be 3 seconds. So it's like 160 times slower to do this naive implementation of recursion instead of using this really smart dictionary thing. So this one is 160 times ish faster than the other way. That makes a huge difference, right? That's very big. Okay, and so that's another application.